Objective 8.5, the number e. In Objective 8.5, we want to be able to simplify expressions that use e. We want to be able to identify exponential growth and exponential decay in functions that are using e. And we want to use e to set up and solve continuous growth problems. So first of all, what is e? E represents an irrational number, very much like what pi does. The e is simply a symbol that represents a number, just like pi is a symbol that represents a number. Pi is actually a Greek letter. So we're using it as a symbol to represent a number that's very difficult to write. Same thing with e. And just like with pi, since we know pi is approximately 3.14, we can use that to get approximate answers. Well, e is approximately 2.7. So if you're ever actually trying to get a numerical approximation in a problem using e, you can always substitute 2.7 in and get a good idea of what the answer would be. E is sometimes called the natural base e, and that will make more sense when we get into the logarithms. It is also sometimes called Euler's number because it was discovered by Leonhard Euler. Alright, so one of our objectives is to just be able to simplify expressions that use e. Well, as we just said, e is just a number. So if you have an expression in which e is the base being raised to different exponents, we can still apply the same exponent rules we've always used in order to simplify these expressions. So we have the same base of e squared times e to the fifth means that I can just add my exponents together since I have the same base, and so that's going to simplify to e to the seventh power. If I'm dividing expressions that have e's in them, then I'm going to cancel the common factor from the numbers, 12 and 3, and for my e terms, I can just subtract the exponents. So the 12 divided by the 3 will give me a 4, and the 4 minus the 3 from my exponents is going to give me a 1. So 4e is my simplified answer for part B. In part C, I can use the power of a product property to separate the 5 and the e to the negative 3x, take the square of each of those. Then I can use the power of a power property to take the negative 3x times 2 and make that a negative 6x exponent. Notice I've also gone ahead and worked out the 5 squared here to make it 25. And then finally I can use the negative exponent property to move the e to the negative 6x into the denominator and make my exponent positive. So 25 over e to the 6x would be the final simplified answer to part C. Now in this next part, I'm going to show you the keystrokes to use for different expressions on a TI-84. If you have access to a TI-84 at this moment, pause your video for a second, go get it, and follow along as we go through the expressions. If you don't have access to a TI-84 at the moment, then you can do one of two things. One thing is to go ahead and just kind of watch through this section, and then when you get to class, next class, borrow one of my TI-84s and go back and replay this section so that you can follow the keystrokes and see how to put it into your calculator. The second thing that you can do is get any type of scientific calculator that you do have access to, and after you watch a couple of examples here, see if you can figure out how to make this work on your calculator. The keystrokes are probably going to be close to the same or very similar, if not exactly the same. So you should be able to figure out how to use it, and you do want to know how to evaluate things on a calculator because this will be helpful in upcoming objectives. Okay, so let's go through a couple of examples. Let's say I want to know how much e to the fourth really actually is. Get an idea of just what that amount actually is. Well, this is how you would type it into your TI-84. You would first have to hit the second button, which is that blue button, usually blue, and then you need to find the button that is labeled with the e to the x. That's probably going to be above the button rather than right on the button. Okay, so second and then e to the x button, and then you're going to push 4 because that's our exponent here. So you push 4, and then you need to push the right arrow key to get you out of the exponent spot. So if you notice when you type the 4 on a TI-84, it actually looks like it's up in the exponent spot. So you need to move your cursor out of the exponent by using the right arrow. And then you can push enter, and you should get an answer that looks something like this. Now, even if your keystrokes are different on a different calculator, this is still the answer you should be getting. So if you're not getting this answer, you're not using the right keystrokes. Okay, let's take a look at another one. If I want to know how much e to the negative 0.09 power is, again, I need to find the second button first. So I'm going to push on the second button, then push on my e to the x button, and then this is actually 4 different buttons here. Negative 0.09. All of that's going to get typed in before you hit the right arrow to move out of the exponent spot. And then you're ready to hit enter, and hopefully you get an answer that looks like this. Okay? Alright, so let's try a few here on your own now. Go ahead and pause the video for a moment while you work these out. For the first 4, you should be doing these without a calculator and just use simplification rules and exponent properties. But for number 5, go ahead and use whatever calculator you have access to see if you can get an answer to e to the 3/4 power. Then you can come back when you're ready to check. Alright, so in number 1, we have e to the 7th times e to the 4th. That means we just need to add exponents to simplify our expression to e to the 11th. In number 2, we have 24e to the 8th over 4e to the 5th. We're going to simplify the 24 over 4 and make that 6. And then we're going to subtract the 8 minus 5 to get e to the 3rd. So 6e to the 3rd is our simplified answer. In number 3, we're taking 2e to the negative 3 times 6e to the 5th. Now, if you remember from previous types of problems, this means that we can multiply the 2 times the 6 to get 12. And then when we multiply the two e's, we will add the exponents to get e squared. So 12e squared is the answer we're looking for. And in number 10, we're going to use the power of a product rule, we'll use the power of a power rule, and then if we still end up with a negative, we'll need to use the negative exponent rule in order to end up with an answer of 1000 over e to the 12x. And finally, if you put e to the 3/4 power in your calculator correctly, you should get an answer of about 2.117. All right, so now that we have a little idea of how to use E, let's talk about it in exponential situations. You can still have both growth and decay in exponential equations using E, but the equation looks a little bit different than what we're used to. You'll notice here that the equation is that y equals a times e to the rx power. So now it's not the base that's going to change. The base is always going to be this e, which is about 2.7. So that seems like we're always talking about growth, but that's not necessarily the case. We can also have decay when we are talking about using E. So how do we know when it's growth and when it's decay? It all depends on the R. Our A value that's out in front still always has to be positive. But the R value is what's going to tell us whether we have growth or decay. If the R is positive, then we're talking about growth. If the R is negative, we're talking about decay. And let me show you why that works. If I choose a positive R value, let's say a 2, and I'm just going to keep A really simple by making it 1. So it's still greater than 0. We're just going to have that be 1. Okay? Well, I could rewrite this equation by splitting up the e to the 2x as e squared and then to the x power. Okay? So then I could actually evaluate what e squared is, and 2.7 squared is about 7.29. And so now we have a form that looks more like the exponential functions we're used to. Here's our a, right? Here's our a, here's our b, and here's our x in the exponent. And obviously b is greater than 1, so this would be growth, which is what we were saying because 2 was positive. But now what if I choose negative 2 for my r? If I go through the same process of splitting this up and making it e to the negative 2 and then to the x, that negative 2 now changes my e to the negative 2 into a fraction. And so it's going to be 1 over e squared rather than just e squared, which means I'm now looking at 1 over 7.29, which is obviously a number that is less than 1. And so that's going to make this a decay equation. Okay, so in these types of situations where you have exponential growth or decay with an e in it, it's not based on your base anymore, it's based on the r. Positive r is growth, negative r is decay. So what do you think about these situations? We have 4 equations here, and I want to know if it represents exponential growth or exponential decay. So in the first case, we have y equals 3 times e to the 0.4 x power. What do we need to look at to know if this is growth or decay? All we need to look at is this number right here, 0.4. Is that positive or negative? It's a positive number, and therefore this is a growth equation. How about the next one? Y equals e to the negative 0.5x. Now we have an r value that is negative, and so that negative r tells us that we have a decay equation. Next equation is y equals 1/4 e to the x. Now don't let the a fool you. It is not the a that tells us anything. This fraction is not what makes it growth or decay. What makes it growth or decay is the r. And in this case, what is the r? Technically, it's just a 1. Is 1 positive or negative? It's positive, so we have a growth function. And finally, y equals 5e to the negative 2/3 x. We can see that our r is negative, and so that represents a decay function. So that's really all you have to look at, is just what your r value is. So why don't you go ahead and do a couple on your own. Take a minute to look at these two equations and decide whether we're talking about exponential growth or exponential decay. Pause the video for a moment if you need to. All right, so hopefully you figured out that our first equation has a positive r, so it's a growth function, and our second equation has a negative r, so it's a decay function. Finally, one actual application of this E type of equation is in something called continuous compounding. It doesn't happen very often, but it is possible to compound something continuously. We've already talked about compound interest with quarterly or monthly or daily, but it is possible to compound interest continuously, which is theoretically like trying to say you are compounding every instant. Kind of a weird idea to get your brain around, but that's the idea behind it. And so in this case, we're still using that same format, but instead of an A here, we're using P. That stands for principal, which is the same as initial amount. We still have e to the RT, and so we're using t instead of x again because we're talking about time. And the y then tells us what we're going to get in the future. So if I have a problem like this that says that you deposit $4,000 in an account that pays 6% annual interest compounded continuously, you have to find that phrase in your problem in order to use this continuous compounding equation. If you don't see that, then you're back to what we were doing in Objective 8.2. Okay, so the question is, what is the balance after 1 year? So if we write out the formula, it's A or Y equals P E R T. It's the PERT formula. Okay, substitute the numbers we know in. So the 4,000 is our principal, or the initial amount. The 6% is going to be our rate, but we change it to a decimal again, so 0.06 for R. And then our time is just 1 year, so we're going to put in 1 for T. So when we substitute all that in, and then use a calculator to work it out, we should get about 4,247.35. So the balance at the end of 1 year, if you compound continuously under these conditions, is $4,247.35. So you've made just under $250 in 1 year's time. Okay? So go ahead and try these 3 problems. It's all the same situation. We're just changing the number of years. Pause your video for a moment to work these out, set up your equation, work it out on your calculator, and then come back to see if you've got the correct amounts. Alright, so we're depositing $2,500 in an account that pays 5% annual interest compounded continuously. So that tells us it's a PERT problem. We want to find the balance after 2 years, 5 years, and 7.5 years. So when we substitute all of our numbers in, we should get a balance of $2,762.93 after 2 years, a balance of $3,210.06 after 5 years, and a balance of $3,637.48 after 7.5 years. If you're having any trouble getting those answers, make sure you ask questions about it in our next class. Maybe it's the way you're typing it into your calculator, maybe it's the way you're setting up your equation. But either way, I can help you figure out what the issue is. Okay? So this is our last practice and our last objective before our first quiz. So in our next class, you should be able to work on the 8.5 practice based on this information. And then when you show this to Mrs. Gordon to get it checked off, then you'll want to work through the practice quiz 8A to help you prepare for the quiz, which will be over objectives 8.1 to 8.5. Again, if you have any questions on anything you've seen in this video, don't hesitate to ask during our next class. And we'll see you then.